Okay, so right now we're going to talk about the crystal, right? And adding the crystal to our Colpitt's oscillator and what essentially it does and how it makes it more stable. Now, having gone through the notes, right, you should know that the crystal at certain frequencies, right, the crystal will act as a series resonant circuit, and at another frequency, it'll act as a parallel resonant circuit. Okay, so again, the crystal, it's made up of quartz mostly. And again, we saw that it could be made up of Rochelle salt or tourmaline, but we often don't use that stuff. Rochelle salt being the best piezoelectric crystal, tourmaline being the worst, but the strongest. So Rochelle salt is kind of very fragile and expensive, where tourmaline is very hard, but doesn't have as great of a piezoelectric. So like I always talk about in electronics, we're always going to use the cheapest thing that does the job. And in this case, it's often quartz. So we basically, in here, what we basically have is a quartz crystal. Again, it's cut to a specific resonant frequency, right? You specially cut the crystal to resonate a specific frequency, and then you basically put it between two plates, and you got this equivalent circuit on this side. So the key to the operation of this thing is, again, like I said, part of the time we'll say at Fs, it's going to act as a series resonant, which means at Fs, it's going to be basically the equivalent of a capacitor and an inductor in series, okay? At Fp, it's going to act like a capacitor and inductor in parallel, okay? There we go, it's in parallel. So now remember that the key difference at resonance between these two is that this one acts as infinite resistance at resonant frequency, and this one acts as a short. So that's a short. So how the crystal is used essentially is we have all the same parameters. Now note that we have the transformer here, but again, this is just for coupling reasons, right? We're using the transformer instead of our inductor. Notice C1's variable, obviously, so we can change the resonant frequency to whatever we want. But as the circuit comes through, right, so we trigger it, like all oscillators, it gets triggered, right? The signal comes in, gets amplified, gets inverted, right? Goes through, the output is C1, the input gets inverted again, right? We talked about how the inductor and the capacitors act and invert the signal. Then that frequency comes through this. Now in this particular case, it's going to be set up as the series resonant. So if the frequency is bang on, in other words, it's at Fs, for all intents and purposes, this guy's a short. And it just allows that signal to go through, get amplified, and then the circle continues. No attenuation, right? However, if the frequency's off, right, he's going to start showing a bit of resistance. He's going to start acting like a resistance, slightly attenuating. So for instance, if the frequency is off a little bit, the gain comes back a little bit, or comes up a little bit, he is going to come through that little bit of gain in the signal. He's going to act like more of a resistor, right? Suggesting to attenuate the signal slightly more. So what you get here is something a little more constant. Now we talked about, if you go through the notes, you'll see that we implement crystals because of numerous reasons, right? It could be that we change the transistor, right? So if we change any of the components, so you can imagine if the crystal wasn't here and all you had was a feedback network, if you change any of these components, right, the balance of the circuit gets compromised, okay? And also note that temperature also affects everything. So if I change the transistor with another one, we know that all transistors don't have the same beta. So then the gain is changed, and then everything goes, you know what I mean? If you didn't have this feedback back, then everything goes out of whack. Same with all these reactive components like the capacitors and the inductor. If you change anything here, there's no guarantee it's going to bring it back to the way it was. So what we do to stabilize the circuit is we add a crystal that basically acts as a variable resistor at certain frequencies. Provided it sees its resonance frequency, it's perfectly happy, lets the signal go through. If it's not, it acts more resistively, attenuating the signal more.